CorrLog, Correlated Logistic Model for the Introduction of Multiple Labels, and it is by Wei Bian, Xie and Dacheng Tao.
Yeah, thank you. Today I'm going to talk about multi-label classification by using correlated logistic models, and this is joint work with Xie and Dacheng Tao. Multi-label classification arises naturally from real-world applications. Take image annotation with multiple objects. For example, an image can have different kinds of labels, just like a key, C, or both. And similarly, text categorization with multiple topics can also be regarded as a multi-label classification problem. And formally, suppose we have m labels, and each instance x has a label vector y belongs to the label set minor 1, 1 to the power of m. Then multi-label classification, MLC, aims to learn a decision function which maps from the instance space x to the label set y. A straightforward way to do MLC is to convert it to a multi-class problem. However, this is a bad idea because it needs exponential number of classifiers to do classification. And also there are regression-based methods for MLC. Basically, it maps the discrete label vector y to a real-valued vector space z, and then do regression. After that, it recovers the label vector y by doing the inverse mapping. The optimal decision function should be optimization over the conditional probability py given x. So it is natural to do MLC by directly modeling the conditional probability. If we know the correlation structure between labels, for example, if the correlation between labels span the tree structure, then we can decompose the decompose the conditional probability into this product. However, if the structures are unknown, then it is more difficult because it is hard to parameterize the conditional probability over the entire instance space X. And therefore, there are some others to model the conditional probability given X locally, or there are intuitive methods called classifier chains. So in this work, we want to propose a very easy way to model the probability, to model the conditional probability py given x, and here is the formulation. We call this the correlated logistic models, and CorrLog for short. By the graphical model representation, we see that the CorrLog is simply a special case of conditional random field. However, it is so simple so that it's better to view CorrLog in another way. If we restrict all the correlation coefficients alpha to be 0, then it's easy to see that CorrLog degenerates to independent logistic regressions. So CorrLog is just an augmentation of independent logistic regression by considering only the second order correlation between labels. And another thing worth mentioning is that the augmenting factor Q is exactly a function over label y. However, it is not a prior over y, so that it cannot be learned separately from the model. And the learning for CorrLog, a straightforward way to learn CorrLog is by maximal likelihood estimation. However, it is intractable because of the partition function. And although sampling method or approximate inference can be applied, they are not very efficient when the label numbers are large. Therefore, we tend to use pseudo likelihood method. The pseudo likelihood can be read as the product of the conditional probability give each labels given by all the rest of labels. And in our case of CorrLog, this component probability is just a logistic regression. So, if we have n training examples, the parameter of CorrLog can be learned by regularized pseudo-likelihood estimation. The learning procedure is very efficient. We can use a gradient descent-based method, and we can show you that the computational complexity of the learning procedure is linear with respect to the number of labels, so that CorrLog has a very good scalability. Further, we can also use accelerated gradient descent method to speed up the training procedure. For prediction, given a test example, the prediction of by CorrLog is an inference problem over the Ising model. However, although it is an Ising model, the inference is much easier. This is because from the factor graph, we can see that these factors, beta I and x, provide a basic probability for each of the labels. And then the correlation factors just adjust each of the labels so that we can get a joint prediction. So we can use this one to get to make a initialization and run the max product algorithm to do inference. Since the algorithm does not necessarily converge, we use early stopped. And empirically, this inference works very well. I think it is most because the correlation factors are very small and nearly sparse, so that the graph is very nearly sparse. Although it is not a good idea to use inference to do prediction, but it has some advantages. For example, the inference can predict all possible label vectors, even that not appeared in the training dataset. Yeah. In the next part, we want to give a generalization analysis of the proposed CorrLog. Before we show the proof, we have some considerations. First, the learning of the CorrLog is not based on empirical risk minimization, but by pseudo-likelihood estimation. And the second, we want the bound to be the generalization bound to be independent of number of labels, so that CorrLog can be applied to large-scale problems. And the key tool we used in our proof is the stability concept. Here, the capital D is a training data set, and D to the power I is a slightly change of this training data set by replacing the S training example with an independent example, so that the stability of an algorithm with respect to the loss function L basically says that the testing error over any examples does not change very big when we slightly change the training data set. Basically, the stability of algorithm says that the variance of a learning algorithm is small. So we can use this to derive a generalization bound on the testing error. The testing error is bounded by empirical error plus a residual term that is determined by the stability eta. For multi-label classification, especially for CorrLog, we define the loss function as below. Here, the decision function is defined as the difference between the log likelihood evaluated as the under truth label maximum log likelihood evaluated all other kinds of labels. Therefore, if the decision function is less than 0, we get 1 loss. If it is larger than 0, we get 0 loss. However, this advantage of this loss function is that it is discontinuous. So we slightly change it by introducing a margin gamma. Then if the decision function is larger than gamma, we have no loss. But if the decision function is smaller than gamma, we have this 1 minor f over gamma loss. I'm not going to show the details of the proof, but I try to give the roadmap. We have two components. First, we use the strong connexity of the objective of CorrLog to show that the Lund parameter does not change too much if we slightly change the training data set. And then by the Lipschitz continuity of the loss function we defined above, we show that the testing error does not change too much if the parameter changes a little bit. With these two components, we obtain this lemma, the stability of CorrLog. It says the testing error does not change too much if we change the training data set a little bit. With this lemma, we finally obtained the main theorem. It says that the testing error is bounded by the training error plus this term. And on this result, we have two comments. The first comment is that the generalization bound is independent of label number, but it does not mean the performance of CorrLog is independent of label or number, because here is also the empirical error. The empirical error can be very large if the number of labels increase. And the second comment is that the L2 regularization is necessary to obtain this kind of generalization bound. This is because we need the strong convexity of the property of this objective of CorrLog. Next, here is the example tie. In order to show the power of CorrLog for joint prediction, we design this kind of tie. Here is a two-dimensional space, and we sample the examples uniformly from the unit circle. And we try to we give each example two labels. And the first label is determined by this line, this dashed line. And in order to introduce correlations between labels, we use this OR operation. It means whenever the first label is positive, then the second label is also positive, so that we can see in this area the labels of the instance is plus plus but not plus minor. And this middle the figure here shows the prediction result by using independent logistic regressions. Since it does not capture the correlation between labels, the prediction is not very good. Only this decision bound between only the decision boundary for the first label is correctly predicted, but for the second label, the prediction boundary is totally wrong. And originally there are only 3 kinds of labels, but in the prediction result by independent logistic regression, there are 4 kinds of labels. And for CorrLog, the prediction is almost the same as the under truth, and we only get a 6% error. but with independent logistic regression, we have nearly 20% error. We can also see that the prediction boundary of CorrLog is nonlinear. Although this example shows the advantage of CorrLog on joint prediction of multiple labels, it also shows some drawbacks of CorrLog. This is because we can see that we still have 6% errors. Where does this error come from? From the definition of CorrLog, we know that it only captures the second-order correlation between labels, and it is also follows a symmetric formulation. We see it means the correlation between yi and yj is the same for yj and yi. But in the data generation procedure, you see that the two labels are not symmetric. The second label y2 is affected by the first label y1, but the first label y1 is not affected by the second label y2. Therefore, the data is not symmetric, but the model is symmetric, so that we get this 6% of error. Then we used 6 real data sets to evaluate the performance of CorrLog. They are benchmarks in multi-label classification. The sample size and the data dimension varies from 100 to 1,000, and for the label, the maximum number of label is 53 in our experiment. And we use three measurements to evaluate the performance of different algorithms. The first is the Hamming loss, which counts the misclassification of error base of label, and the 0-1 loss counts the mispredict of entire label vector. And also we use L1 score, which is harmonic mean between precision and recall. First, we compare this CorrLog with independent logistic regression, because this shows how much gain can we obtain from using from second-order correlation modeling. This figure shows the Hamming loss. This one shows the 0-1 loss, and this for F1 score. We see that on these two we obtained a very big improvement. For example, on this data set we have 10% 0-1 loss improvement. However, on the Hamming loss evaluation, it does not show much improvement over the independent logistical regressions. And even worse, on two data sets, CorrLog show worse performance than independent logistic regressions. Why is this? Does this mean the independent logistic regression works very good on these two data sets? The answer is no, because we tried to use a dumb classifier which classify the labels of instance to -1, no matter what the untruth label is. And so we get a Hamming loss of 0.044 on this data set and 0.06 on this set. The performance of the dumb classifier nearly works as well as these two models on these two data sets. And for the comparison with other methods, we use 3 algorithms for MLC. This one is instance-based learning by logistic regression, and this one is multi-label KNN, and also we use classifier chain. From the table, we see that on these two measurements, CorrLog always works better than other methods. But on Hamming loss, it does not show too much improvement. Sometimes it works worse than other methods. And here is the result for the other 3 data sets, and the same conclusion we can draw from the table. So conclusion. In summary, the proposed CorrLog is an efficient algorithm for multi-label classification, and it has a linear computational complexity with respect to the label of numbers. And it also has a guaranteed generalization ability, which is independent of the label of numbers. Both of these two properties indicates that CorrLog is a good algorithm for large problems. And in the future studies, we have two directions. First, CorrLog, the alpha learned in the CorrLog is dense, though it is could be very small. But since it is dense, it has not very good interpretations. So that in the future work, we want to restrict the alpha to belong some interpretable model class, such as the tree class. And also, we want to extend the CorrLog to temporal signal modeling, such that we can use it to do cause recognition from musical signals. Yeah, thank you. That's all.
Time for questions.
So I don't quite understand what you mean by guaranteed generalization ability. Are we taking some, it seems like... So you mean by independent label?
Yes. This guarantee does not mean on every data set, CorrLog has a good performance. But it means that the difference between testing error and the training error could be small. It can be bounded. If the training error is still larger, then the testing error is also larger. Yeah, I think this is the answer. Thank you. Okay.
Yeah. So one other thing I didn't understand is that this test time inference procedure is not guaranteed
So,
to be.
okay.
The test time inference procedure is not guaranteed to be exact, right?
Because this is an inference problem, and the graph is not a tree. This is have some loops. But we can the better things happen here is that we can use this factor to do initialization. And since the factors on the right is mostly small, then the iteration numbers is small.
Right, but since you don't write any guarantees on how well inference...
we don't have any guarantee.
How does that reconcile with the generalization about where you can make a strong statement about testing?
You see that the generalization, the loss function does not depends on the inference procedure, does not depend on prediction procedure. It is calculated by the difference between the log likelihood evaluated under the under-truth label and minus the maximum likelihood evaluated at all other labels. It does not depend on the inference procedure.
Okay, so this assumes you can do exact inference.
No, not that case. We can, when we obtain the testing, the predicted label, we can use this one to recalculate the training error, right? If we know the under-truth, then we can recalculate the training error.
Maybe we should take this off.
Okay, I can explain this to you after the section. Yeah, thank you very much.
Somebody had a question around there. I see you're using zero likelihood, which is fast to estimate, but it is sometimes gives rise to severely biased estimates. Have you considered running a Markov chain?
I haven't tried that, but I'm not sure if it works better than pseudo likelihood. Honestly, I haven't tried that.
final food. Okay, then this concludes the session. Let's thank all speakers.
Yeah, thank you very much.